so I can have just a little white on my finger to make it look like heavily cratered. And here's something called the weird terrain. Support. Hi, welcome to. First, I would like to show you that all my content on audio streaming platforms like Apple Music or Spotify. Audio only to some of my content. A lot of. So just type in ASMR. Today I would like to draw a net. And I haven't done this before, so actually I think it will end up in two maps, one for each side. I will start with one side here, and then the next one I will do the opposite side. What I would like to draw is Mercury, the planet closest to our sun. So we have the sun and then Mercury, the smallest planet in our solar system, smallest of the four terrestrial planets. It's smaller than the gas giants that are further out in the solar system. And it's a bit bigger than our moon. It's smaller than Mars. It's actually smaller than two in the solar system, moons for orbiting around Jupiter and Saturn. So here on the South Pole here, and I prepared this paper with just black ink. And I try to add some white ink, because it's to me it looks, the pictures I've seen of it, there are lighter parts and there are darker parts. So let's see how. Just use this type of tool. It's not a brush, even though it looks like a brush. Gray color also, areas. So I will start with the side of Mercury that has impact basin, the biggest impact basins in the solar system. The Caloris planet. It's easy to do like this. This side of the planet seems darker, and the surface is older actually. And there are some very bright spots that has rays like this, extending for several, even thousands of kilometers, I think, in some cases. So all crisscrossed with these types of rays. And these craters, because these are also craters, the youngest. I want the colors to blend more, not like being too separate. See if we can. lighter. I'll keep it darker here to the south. And this consists of a very smooth floor. There are a lot of planetias where the floor is more smooth and like the rest of the planet. For example, the Lubus Planitia here, Sobku Planitia, and Catuilla Planum, Tyr Planitia. And I think this got too big. And here, very dark area around the Tolstoy, so a very old part of the surface. The reason for this difference in the dark areas and lighter areas is that more recent impacts from armor bright causes the material under it to totally crash. Also, it releases so much energy, so the crushed like powder of this rocky material will like just, and it will like create this rays of lighter. Actually, it's lighter because it's fresh somehow and crashed. Then after time, particles from the like solar wind or just particles will make these brighter areas darken. Which craters are the youngest ones? It's those who are, if they're very powerful impacts, then very long rays, extended rays in all directions. And then inside the crater, sometimes like Caloris Planitia, or this huge impact here, it was just like the other old surface of Mercury. It was heavy from the time when it was heavy bombarded craters all the time, like the first billions of years since the creation of everything. During the first, the creation, the forming of our solar system took place 4.6. During the first 1 billion years, there was, when all the planets and moons and everything formed, then it was these comets and material for planets and asteroids. Then around a billion years ago, it stopped. The last phase of this was called the late heavy bombardment. And it's been calmer, and but occasionally there, of course, and there has been impacts. But then you can see that there's a result in volcanic activity, Mercury. So then the lava will come out of the planet and create it will fill the crater. So it sometimes in this still see even newer craters, but just like the old area. So here, for example, I can see 3 from, or yeah, at least 3 that are a bit bigger. And since this impact basin, the impact was so powerful, Mercury can be found here at the edge of the rim of this crater, are called the Caloris Montes, and they are kilometers, I think, tall, miles tall. And it's not that tall at all, actually, because you can compare on Mars to 22 kilometers high, or the highest mountains on Earth, Mount Everest, if you count from 9 kilometers high, or Mauna Kea, Hawaii, that counts 10 kilometers actually, base to peak. And that's interesting because you compare it like this. Why should you consider Mercury? There is no sea level, so you count everything from to peak. So in that case, Mauna Kea is that on Earth 10 kilometers compared to the more than 2 kilometers. And the reason why there aren't so high mountains on compared to Earth, there's a big difference. There are no tectonic plates here, and the tectonic plates where they're moving, all these moving plates who collide mountain ranges on Earth, that doesn't take place here. So the mountains can just be impacts like this. But there is actually another way created on Mercury, and has been created on Mercury, because of its gravity, because it's a very small planet. It's just 200 kilometers in radius, or 1,500 miles. Only a third of the Earth radius, or 38% or something like that. Core, compared to Earth. Its radius of Mercury is the core, and on Earth it's only 55% of the Earth. It's like made of iron and metal, liquid, liquid. And then the mantle and the crust is just very thin, like this. Has a super high density, and gravity is very strong on this one. And that resulted in something strange, that when all those late heavy around 3.8 billion years ago, then as the planet cooled down, because the volcanic activity kind of stopped also, because it was the impacts of volcanism. So then it started to cool down on this, caused by this giant core, made the planet crust shrunk like this, several miles. And when it did that, it actually helped the volcanic, it was a reason for the volcanic activity to stop because rifts somewhere, and they were like squeezed together, so it stopped for the magma to reach the surface. It became, then there were like rifts created, or cliffs like this, where the crust. Many places on this planet you can find something called the rupes. It's Latin for cliff or something like that. And those are several miles long, so they can be approximately 1.5 kilometers high. Now I'm mixing. Let's see. Yeah, the longest rupes is 510 miles long. These rupes are something like 1.5 kilometers. And what would that be in miles? I think 1 mile. Now let's go on with some outline. And I'll use this white ink for that. I was thinking about drawing some craters, because basically there are craters and craters and craters, and some of these rupes. Fontaine crater. And the craters are named after famous authors and musicians. Fontaine, for example, is named after an English ballet dancer, Margot Fontaine. And then add Radiclade is a young crater, probably only 1 billion years old, and that's young when it comes to, most of the surface was already finished, so to say, after the light heavy bombardment. So then the younger impacts can be like 1 billion. So Radiclade is a typical peak ring crater. It's more like one ring and more further out. So it's like probably it had resulted in volcanic activity and effusive volcanism. That's when it's not volatiles included in the so they are a bit more calm, not explosive. Yeah, they're called effusive, and it's more like slowly floating lava. This inner ring here is solidified lava from the volcanic eruption caused by the impact. It's more older surface. Yeah. There's a crater here and rays, bright rays. Not sure if it's the Eastman crater or if it's a but I'm not sure if that one is the bright one or if it's a smaller to the west of Eastman. And crater. Another crater in the southern hemisphere. A bright crater here in the southern hemisphere. Some rupes, the Beagle rupes. It's one of the rupes on the planet, and they are located here west of a crater called the crater, named after, I guess, an Icelandic artist. It sounds Icelandic. Here is the Catuilla Planum. This area is called. The planum is a plateau or high plain, and it's named a word in the language Quechua. It's the Quechua word for Mercury. And actually, all the planetias, planetias are long planums, they are named after the name, as you'll see. And here's a small Vonvo. Are the Paramur rupes. Rupes, the escarpments, that's of famous explorers. Alvin rupes. Is a bright young crater called one of the craters with extended rays. I think actually the best choice for drawing these arrays. Then, yeah, here, this crater I will probably, it's on the side here. You'll see it from the other hemisphere too. The Rembrandt crater, the second biggest crater. And here is Granger crater, Shergill crater, Ruda crater, the Hero rupes, and the Dostoevsky crater, big crater here, Basho crater, and here, dark because of, it's very old. It's a Tolstoy crater, also quite a big crater. 400 kilometers in diameter. The Basho crater also has some quite prominent rays from it. East. It's another very large crater. It's the planet's third largest impact basin. Actually, when it's bigger, the craters in diameter, or 180 miles. And Beethoven, as you could expect, a ringed crater. The larger impact basins are quite often, and that means that they have concentric rings. You will see, for Planitia, the largest basin. That's like, if you study it close, some rings starting a bit away from the center, and then they're like the ring crater. West of Beethoven, Jufken Rupes, Jufken. And here's a smaller crater, but with bright. Here, to the east, Logos, equivalent of Mercury. And Mercury, he was the messenger god, and he had to always travel between humans and the gods. So the Greeks named this planet Hermes, and I think it's still called Hermes. It was their equivalent of the Roman god Mercury. And the fastest planet, having the fastest speed in orbit. And in ancient times, when they went up, they could only see it close to the sun, and from Earth you can still only see it very close to the sun. So, it's like never further from the sun than 28 degrees since it's the Earth. So it's another, just like Venus. It's a morning. It has been called the morning and evening star, and it has been very fast to observe it because you have the sun so close, and it's difficult to see the surface of Earth. But Logos was the Gaulish equivalent of Mercury god. Let's go through the planetias now, so I don't forget any. Bud planets into word for Mercury. Caer planetia, the Irish word for Mercury. Planetia is here. Ancient Greek name for Mercury. Make it Hermes, I guess. Odin's god. It's not the equivalent of Mercury, the messenger, I mean. Or there is no messenger god in Norse mythology. Tyr planetia. Tyr is a Persian Mercury. And is the Japanese word for Mercury. So we say here, here's Subko, the ancient Egypt messenger deity. In Logos waters. Ray system. And here's is the crater Vieira da Silva. But actually it's the crater inside, the smaller, newer crater inside of Vieira da Silva. That is the raid one. So you can see rays coming. Crater as well. Here in the Subco planetia there are Bronte, and also from Deca there are several rays. And here there's a feature that I don't know what it comes from. You can see it's a bright area line that is somehow curved. And in Asia, I would like to draw 3 craters that are even newer inside this basin. And also, here's an area called the Pantheon, and it's an area with. They should not be bright. I should not draw them in white. But it's another quite unusual feature. This place was the spider. It's like radial lines from one point here, but they are like dark lines, so I will not. And here's Balzac creature and Tiagaraja. Also a bright one. Those 2 craters also have a feature called hollows in the center, caused by some volcanic activity, magma, and again, or like it was the crater was drained after maybe long. There were still some hollows that collapsed, and you can see like so it's like a rest from on the smooth the floor, but angular from this point of view. And here in Swiss, it's a big crater called Shakespeare. Actually, here I want to include it because I know it's a Swedish writer. It's this crater called. It's a crater. It's a very small crater called. But it's very important, I think, this crater, because I read that very close to Janacek crater, their messenger crashed on the surface of Mercury in 2015. There have been 3 spacecraft launched. The 3rd one is still on its way. It was launched in 2018, and it is planned to run Mercury in 2025. So that will be very interesting. But the first one was early 1970s. It was the Mariner 10. In 1975, it orbited 3 times around Mercury, and 45% of the surface. Unfortunately, because the Mercury day compared to an Earth day, so unfortunately it could only map the same part. I know that only half of Asia was covered. And then in 2008, the next mission. By the way, Mariner 10 after in 1974, 1975, it just continued and still, but the gravity and the heat and everything then made it not working anymore. So you can't get any. I mean, the instruments and everything is. And the Messenger, and it was orbiting Mercury for 4 years, and from that satellite, there we had now had. So that's when Mercury finally became mapped. Ended with a crash here, close to Yanache crater. So that's where it's now. And here, on the eastern rim of Caloris Planitia, are the Caloris Mountains. Or mountains in planets are called montes, or I guess mountain ranges. Montes. Mountains, like Olympus Mons, are called Mons. And these are the tallest mountains on our planet. I guess the other side. Lines and cracks here, so I can see the photos. And west of Shakespeare crater, also Zeeheim. Oops. And here in the T Planitia there are also 2 newer craters with some rays. And from the Eastman, rays both from Fontaine and almost meet. So here it's actually a very bright area, this area here. Around rays. So rays. Then of course there are a lot of unnamed and also more named craters. The surface of the entire planet, I mean, is about 75 million or 46 million square miles. And to the entire land, Americas, North and Central, or South America, and Africa. Those surface areas together is also around 70. And it's like that half of the land area. But the Earth is much bigger because it's only 29% of all area. The rest is. And if you put the entire Eurasia continent and Oceania and Antarctica together, so those 3 also makes 25 million square kilometers. Now I think it's time to move on to the next side of the planet. One thing, I would like to draw the outline of the planet as well. Okay. Perhaps. And now to the next one. Caloris antipode. Also, this hemisphere has darker areas. South and to the west. And there are these very light plains, Realis, Planitia. To the northern plains. And the Rembrandt crater. Let's see. Hokusai crater, brightest of all craters. Plains, there are the Sihto plain, Torms, Planitia, Barangi, Planitia, and Utaridi peninsula. I need to blend it a bit more. Just a little white on my fingers. Heavily cratered, the old cratered area. And here's something called the weird terrain. Make it look weird. Big crater called Rachmaninoff. Okay, now we'll go on with some so let's continue with craters. Here on the western part there's Prax, quite big crater. So it doesn't. Also Rachmaninoff on the eastern part here. Crater. In the middle, probably the magma that had floated up after the impact, and that where the lava didn't reach. It was like floating up and not exploding so much. By the way, explosive volcanic is more common when there are. Maybe I already said. I think I mentioned that before. But I guess there aren't so much water, at least not now, because it has no atmosphere. So for a long time there were no water, I guess. But now actually they have discovered some water ice-filled craters in the poles. The temperature never gets higher than something 93 degrees or minus 136 Fahrenheit. It can still be contained in those craters as ice form, solid form. But the whole surface becomes very hot during the days, and I guess because of that, no atmosphere. So I think the volcanic activity is more effusive, or just lava, and not this. Maybe what do you think of when you think of that explosion? And here's a bright crater called Soyuz, named after the famous children's book author, actually. Picasso. Pit craters, or pit crater is another name for the type of crater hollows, the pit in the center, that may have been a volcanic vent. Ellington, it's double. And close to Ellington, it's also a peak commonly dark compared to the brighter Ellington. Holst, Nabokov, another crater. David system. The most bright ray system is Hokusai in the north here, Provincia. Very bright. I think I need a lot of it. Probably I can do this. That spot here, I don't know what crater it is. Below is also very deep. It's the deepest place on the whole planet. It's deep, or 5 kilometers below the global average. The central basin here. Filled now with lava, I guess. And it's 290 kilometers in diameter, and one of the most recent craters. So Rachmaninoff in size to the crater just a bit. I showed it on the first one. The Raditladi. These are both young craters. Hokusai is also a young crater. crater. No, let's take this. The second most prominent bright crater in the southern hemisphere. So we have rays all the way from Hokusai to this, and the rays from the sea. Hitomaru crater here somewhere, and another bright crater, actually not named after an artist or musician, astronomer Kuiper, that also has in space. Kind of another crater called Murasaki. I think Kuiper is the brighter one with these prominent rays. Crater in quite dark surroundings. Homer, a peak ring crater. And Raphael, it's a very big crater, but not multi-ringed, so all big craters are not multi-ringed. Another big crater. Schubert. Cavalry Rupus. Quite a long Rupus here, 500 kilometers long. 0.5 kilometers high. West of Rachmaninov crater, so there are some Rupus, the Calypso Rupus, on the photo of this area. And also here to the very east there are some Rupus. And that's actually the longest on the planet, kilometers, or 510 miles. There, very big crater, Rembrandt. Biggest on the planet. I showed you part of it on the other map. And it's a young crater, so it's quite bright, and I think it is 8 meters in diameter. Smooth plains in the center and terrain in the surrounding. And the Enterprise Rupus actually crosses the crater, and that's why the Rupus were created after the crater, because they cross the crater. Then the scientists realized that this shrinking process that results after this late heavy bombardment, because all the Rupus are like, I guess, most of the craters, if not all the craters. And here's a crater called. And here are some more Rupus. Rupus. And Hedwana. And another crater called Dershavin. Holbein. Monet. Rodin. Molière. In the very center of, at the equator, longitude 0 degrees. I think it's 80 degrees, not sure. But in the very middle of this map, it's a bright, smaller crater. Trying to extend the rays like this. Should it be this bright? The system where this bright area. I'll try to make some of these craters a bit darker, because I think there's a. So if I just put a bit of ink on my finger, try to darken them. This one should be quite dark. These ones. This one. I think Kuiper should be a bit more bright. And here there are some rays crisscrossing. I was mentioning, because the area in the very center, both at the equator but also at both longitude 0 and longitude 180, it's actually the hottest areas on the planet because of the weird or very unusual orbit that Mercury has. I thought it could be nice to explain the orbit a bit. So if this is Mercury and this is the Sun, or we can put it like this, and it's not according to scale, of course, it's much bigger than Mercury, but it's a quite special way of orbiting the Sun. First of all, with the Sun in a 3-2 spin orbit, and to be tidally locked, it means that the gravity of, in this case, the Sun, in which this smaller planet is orbiting, and the size of it has the rotation of the smaller planet or moon in some cases have like it depends on of the smaller planet. It depends on the direction or which part it's facing, I would say. So for example, the Earth, if now this is Earth and this is our moon, then the moon is tidally locked in a way that it rotates around its own moon. I have put 12 here, so you can see that when I rotate it, like full complete rotation around its own axis. Here in the middle, and it rotates, and it's not flat, it's spherical. I hope you get the point. So exactly the same time the moon will rotate one time around its axis, it takes exactly the same time for it to hit the Earth. And that's why we always, from Earth, we will always see the same hemisphere, the moon. So this, the backside of the moon, we will never see. And I guess it's not a coincidence, and it's, yeah, when a much smaller planet is orbiting a much bigger moon or star, planet or star, tidally locked in some way. And now back to their relation or resonance is 3, which means that it spins 3 times its own axis for every 2 revolutions. And it completes around its own axis every 59 Earth. And a solar year on Mercury, that means a bit around the Sun one time, is 8. So 59 Earth days for spinning like this, 1 revolution, orbit, a complete orbit. But then the solar day on Mercury is actually 176 Earth days. And that be if it rotates around its own axis every 59 days. How can solar day on Mercury be 3 times longer? And it appears on Mercury, if you would be standing on Mercury, it's every 2 Mercurian years. So at 8 Earth days, then the solar day, the time it takes from one sunrise to the next sunrise, the next day, so 1 day and 1 night, that's a solar day. So it takes 2 to complete just 1 solar day. So 1 solar day is 2 years. It's like the years are shorter. And this strange relation between and day is because of this orbit resonance, that it's tidally locked in that way. So strange when I wanted to like think about how can it be like that. So that's why I have a model here. So I will try to show you. If we start, first I want to describe what this is. This is the Sun, and I have just divided the orbit, one complete orbit, pieces, equal pieces. This is 1/3 of an orbit, 2/3 of an orbit, and a 1/3. And this is Mercury. Just so you can see how many 12ths of a complete it has made. So when it goes from upright 12 to the next upright 12, then it has complete solar, or I mean one rotation on its own axis. That's all we know. And it will take 59 Earth days. But this 9 Earth days has no meaning when it comes to Mercury and the Sun, because I mean it has nothing to do with the Earth. It's just a reference for us to feeling of how long a day and a year takes on Mercury. So this solar rotation will actually be 106 days, and I'll show you how it works. So if we start here, let's say this is the first of Mercury, then it starts to rotate around its own and also around the Sun. And here you can see it's upside down, so it has completed rotation around its axis. But then you can see how it's facing. It's actually only to its full. So after, let's continue and see what happens. Now you can see it's back with 12 upwards. So now it has completed around its axis, and it took 59 Earth days. We don't need to care more about that, because as you can see, it's just at 4. So only 4/12ths of the solar day has been completed yet. And it continued to its axis and around the Sun. And then it has complete rotation around its axis. It has completed 1 full orbit around the Sun, because this was where we started. And yeah, I forgot that it's 6 o'clock. So half through the solar day on Mercury. it has completed 2 complete around its axis, and then on the solar day on Mercury. And here it has did 2.5, yeah, 6 is up, so 2.5 revolutions, and it's the solar day. And here we have 2 complete orbits around the sun, actually rotated 3 complete times around it. 1, 2, 3. The first year took 88 Earth days, and the second year took 88 more Earth days, so a total of 176 to complete the solar day, sunrise to the next sunrise. So the days on Mercury, and that's also why the temperature is so extreme, as I mentioned before, I think, which means retain the heat when it goes back into show quite immediately when it turns into night. Those 8 will be much colder, because it will go from very hot today, it can be like 430, 800 Fahrenheit, because it's so close to the sun and no atmosphere, and then during night 180 degrees or minus 290 Fahrenheit. So it's a very big, so it's a lot of extremes. And Mercury eccentric orbit around the sun. It's the largest, it has the largest, I think you say eccentricity, means that the orbit around the sun, it doesn't have the sun in the center. Orbits for all the planets are elliptical, but I think it's more extreme than others, and it's closer to the sun here and very far from the sun here. So this is called closest to the sun, and this is called the aphelion, when it's farthest away from the sun. Million kilometers from the sun here in perihelion, or 29 million miles, and at aphelion 50 million kilometers from the sun, and that's 43 million miles. And it speeds here the velocity when it's closest to the sun, because speed is much higher here, and then it's not so. It has a very quick rotation, quick movement compared to the other planets. And this leads to something that is quite unique, because during some time, then actually the speed of the orbiting meets the speed of the rotation of its axis. And as you have seen, those movements are close to each other, so, but still it moves a bit quicker around its own axis most of the time. But when it comes here, actually the speed of the sun becomes even faster than its orbital, or its axis rotation. Quite fun happens on the surface of Mercury, because then the sun has rise in the morning, and then during midday on some points on the surface, then you will actually see the sun in its movement over the sky, and it will stop, and it will actually go back for a couple of days. And the orbiting around the sun is faster than the rotation speed. Then after some days, now I'm talking about Earth days, just so you can get the time frame, it starts to move in this direction again until sunset. And this whole movement takes a year, so it's 88 Earth days, and then it's nighttime. But that's that at some points where this happens on Mercury's surface, the point where the spot on Mercury, the sun, when it's at perihelion closer, those spots become really hot on Mercury, and it happens at the equator, 0 longitude, or 180 longitude. It's alternating. So there are 2 spots on the planet that can get really high temperature, or whole crater, as I showed you, and also at the opposite side, just southeast of Caloris Planitia, and that's actually why its name means heat in Latin. So this is an area with, so days, but quite short years, I would say. And also it has a orbit plane in relation to the sun. So most of the planets will orbit in approximately the same. If you draw a flat line here, you will find the planets on that line all the time, because they spin exactly. For example, Earth at 6 degrees from a zero plane. I'm not sure exactly how you calculate what's the zero plane. 0 and 1 degrees differs from this plane. So looking farther out you go from the sun, it's more likely that you will find them in very close to the plane. Earth and Venus will be around 1/3 from the plane. Earth is 1.6 degrees from the plane. Venus 2.2. But Mercury, that is closest to the sun, actually have a tilt of 6.3 degrees from the plane. So odd how it rotates compared to the other planets. And then also the tilt of the planet when it rotates is almost totally upright. For example, it has a tilt of, I think, maybe 20 degrees or so. Quite a lot. Tilted to 90 degrees or so. The tilt, it's like not even 1 degree. It's very small. It's types of seasons that you see on Earth, because it's a tilt that causes summer, winter in northern and south. So here it's more other in the orbit that causes different seasons. Yeah, because you can say the night because it's 1 year, and next year you have then you will have the day when the sun is the season. I want to mention this area, the weird. Try to make it look even more weird. The weird terrain. It's of the Caloris planet. So exactly 180 degrees. That huge impact crater. 180 degrees from that, there are some hilly grooves. The nickname is weird terrain. It's also called Caloris antipode. And scientists believe that this was caused by the other side of the planet. That the seismic shock, these waves met up here, converged, and triggered volcanic activity, and somehow caused hilly terrain. Should be some trace there still. Right, this white band, white areas. Too much black ink now. I will just go through the side to see what they are called. Ceto planets is named after the Babylonian word for the planet Mercury. The Turms Planitia around Debussy is named after the Etruscan equivalent of the messenger god. And up here is the Maori word for Mercury. Papsukal after the Akkadian messenger god. And Utaridi is the for Mercury. It's the northern plane. Yeah, finally it became quite weird here, and that was actually what I wanted to. Last thing I will do is to draw the outlines of the planet on this. This is Caloris antipode with the weird terrain. And here's the Caloris planet. I think this one turned out a bit better. I really like the feature plane here. So thank you so much for watching, and hope you enjoyed this video. Found it